Okay, welcome back. We are now finally in a position to summarize pretty much everything we have done so far in this course. And that is how to provide sort of a general rule, um, the set of rules that provides the bulk of quantum mechanics altogether. So before I get started, I'd like to point out to you where this material can be found. And if you look on my webpage here, under teaching, you have a number of lectures. You're probably familiar with this. The fourth chapter is making prediction in quantum mechanics. And it basically contains all of the information I'm going to tell you today about. So whatever I'm saying today can be summarized in these lectures. Okay? Be found in these notes. So going back to us. So basically, in quantum mechanics, the state of the system is identified by, and now comes a new word, and in a second you'll see what it means, by a ray in Hilbert space. And this is identified with a state. So why did I use the word ray rather than just a point or a vector in Hilbert or an element of the Hilbert space? Because you see, this wouldn't be completely correct, because in the end, everything that we can possibly measure is observables. And the expectation values of observable, as we shall see, do not depend on the phase of the wave function, nor on their overall normalization. Let me be more specific. Let's suppose we're interested, for instance, in measuring the probability of finding a particle at X at some point. Well, obviously, what we need to do is to take the square modulus of the wave function at time t. However, you know, wave function can be pictorially represented as a point in the Hilbert space. For instance, this is my state at time t. But the norm of the wave function can always be sort of left arbitrary, provided that when you compute the probability, you normalize the overall norm of the wave function. In other words, you know, you can define the wave function up to an overall constant as long as that anytime you perform calculations, you divide by the corresponding norm. I mean, we've been familiar with this. We did that many times. Either we determine the constant that sits in front of the wave function, that is, we calculate normalization, or we divide by the normalization anytime we compute something. But this arbitrarity of defining these overall constants that sits in front, which can be real or complex, simply means that physical states that are connected by just a stretching of the original vector, so to say, do not represent different physical states. All these points, which are related by another, one by another by a co-multiplication by a constant, they all represent the same physical state. So it would be incorrect to say that states of a system are represented by points in the Hilbert space. They are represented by sets of points that are connected by a trivial multiplication by a complex constant. And this notion of sets of points that are obtained from an initial constant by multiplying it, by the initial state by multiplying it by a complex, is called the ray of the Hilbert space. This is a ray in the Hilbert space. So I hope that now this statement is clear. You can rephrase it by saying this, in quantum mechanics, states are represented by points in the Hilbert space up to an irrelevant multiplication constants. And a given state is represented in quantum mechanics with this symbol, psi. Now, the time evolution of a state is provided by the Schrödinger equation. Right. H is the Hamiltonian operator. So basically, defining a specific physical theory, in the end, amounts to defining what is the Hamiltonian of that physical theory. So this quantity, called the Hamiltonian, ultimately defines the physical theory. Okay, now it's time to make a small digression from enumerating the rules of quantum mechanics, and discuss an important point is, the Schrödinger equation is, in fact, an equation. And in principle, having an equation doesn't guarantee you know the solution of the equation. So the question that I would like to ask myself for a moment is, okay, given this equation, this is the equation that is supposed to give me the wave function at some time t greater than t naught, knowing the wave function at time t naught, the time evolution of the system, let me call it time evolution. So somehow the information about this time evolution is hidden into this magic equation. But is there any way to make this information more transparent, more available, at least at the formal level, to have the wave function, to have something that says, have the wave function at time t greater than t naught. So let's say t is greater than t naught. So let's say I want to know the wave function of t, and I somehow have it like some kind of an operator acting on the wave function at time t naught. And let me call u this operator. And it would be magical if I could find an operator that takes in as input the wave function at time t naught and does the job of solving the Schrödinger equation and evolve the state forward in time until by the amount that I want. In this case, t. to give me back as output the wave function at later time t. So again, pictorially, suppose that my initial state is this one. And then, at some time t, my state is in this configuration. And how you go from t naught to t is hidden in the Schrödinger equation. And it would be fantastic to extract from the Schrödinger equation the information of the time evolution, not in form of a mysterious equation, but in form of an operator that somehow solves that equation. And is such that given its input, the initial state, it provides me directly in output the final state after the time that I decide. So of course, this operator would contain time as a parameter. So this is for time t, maybe for time t half, it will give me this vector here. And so on and so forth. So this operator that solves the Schrödinger equation and evolves in time, the system is called the time evolution operator. And the fantastic thing about the Schrödinger equation is that this operator can be found for every Hamiltonian, and it's given by the following expression. This is how the time evolution operator looks like. How do I know? Wait a minute. Before I tell you how do I know that this is the correct expression for a time evolution operator, let me tell you what I mean by this, because I'm sure you have never seen something like the exponent of an operator. Probably have never seen even the exponent of a matrix, which is the analog of an operator. So by exponent of an operator, so let me write it as a side note. In general, e to the a is defined by the Taylor series. So remember, e to the a is a number now, small a is a number, it's going to be 1 plus a plus corrections and squared divided by 2, a3 divided by 3 factorial. And in general, this is going to be sum from n going to 0 to infinity, or a to the n divided by n factorial, right? Now, likewise, this is sum from n going from 0 to infinity of a to the n divided by n factorial, where a to the n means a multiplied by itself n times. So at least from this point of view, we know what this equation means. So the time evolution operator means that if I want the wave function at time t, all I need to do is to apply u at t minus t naught at the wave function at time t naught. So how do I know that this equation is actually correct? That this is the real form of the Schrödinger, of the time evolution operator? Well, because it obeys the Schrödinger equation. So let's see. If I apply the Schrödinger equation at time t, okay, well, e h bar d by dt e to the negative I h bar h t minus t naught psi of T naught. I'm assuming this is correct, and I'm going to show you that if you choose the evolution operator to be in this form, this equation is always satisfied. Well, now you see t, the time t upon which we are differentiated only enters here. It doesn't enter here because this only depends on T naught. It doesn't enter here because H doesn't depend on T. So when I take this derivative, what do I get? I get I H bar negative I over H bar H E negative I H bar T times T naught. So I get H psi of T. So this equation simply is telling me that if I choose the evolution operator to be in the form specified by this equation up here, then I automatically obey the Schrodinger equation. So in other words, that the evolution operator enables me to construct a solution of the Schrodinger equation. So the evolution operator is in fact the formal solution of the Schrodinger equation. It tells me how the system evolves forward in time, not so much in terms of an abstract Schrodinger equation, but rather as a concrete operator. So summarizing, I can express the dynamics of a quantum system in two equivalent ways, in an abstract way through a differential equation, or I can formally solve this equation and represent the dynamics in terms of the solution of this equation directly, without stating the equation, stating directly the solution. And the solution is that if I want the wave function at time, I need to take the wave function at time t naught and multiply and act on this wave function with this time evolution operator. End of the parenthesis. Let's go, we can continue with the rules of quantum mechanics. Now, that's, if you go back on these notes, that's basically this the first part. Okay, so let's read through these notes and then possibly use the whiteboard if we need further explanation. Any experimentally observable quantity O is associated with an Hermitian operator O with a hat in this Hilbert space. We went through that already. The possible outcomes of the observation of the quantity O associated to the operator hat O are only its eigenvalues, OI. So what does that mean? Is that if I want to measure the observable O, I define an operator. And this operator will have a set of eigenvalues, possibly infinite set of eigenvalues. And anytime you perform a measurement, a physical measurement with an apparatus taking numbers by interacting with nature, extracting numbers, the outcome of that measurement cannot be any value for O, but only the values that are eigenvalues of the corresponding operator. Example, if I measure the energy, then the corresponding operator is the Hamiltonian, and the eigenvalues of the Hamiltonian are the possible outcome of energy measurement in the system. Okay, so let's come to the next point. And the next point being, given the outcome of all these possible experiments, what is the probability to getting any of this outcome? And obviously, this is a generalization of the problem. Given the possible position of a particle in a box, what is the probability of measuring the particle at any of the position? Or given the momentum of a particle, what is the probability of observing the particle with a given momentum? So, this is a generalization of the problem of computing probability of x in time of t, probability of p in time of t, and now we are saying probability of observing more generally any value of the observable quantity O, where O is any observable quantity associated to a generic Hermitian operator O. So in this sense, we are going general here. And the rule of quantum mechanics that determines that is that basically the same rule we have applied for position and momentum, and that is the probability to observe in the system in configuration O, to find in the O if eigenvalue with a measurement at time t is given by the inner product between the state of the system at time t, the corresponding eigenstates. By corresponding, I mean the eigenstates which has OI as an eigenvalue, modulo square. So let's see that this basically corresponds to the rule we already have used. Well, in particular, if I'm interested in observable being position operator, then, my position operator has eigenstates, which are continuously labeled by continuous label x. Then, of course, the probability of observing the particle x at time t is given by the square modulus of this mathematical object. And this is nothing more than the so-called wave function phi as a function of x. And if you have a different Hermitian operator, say p, then of course, so O is equal to p, then of course, all you need to do is to substitute here with p. Now, this will be called phi tilde of p. And the fact that you can go from one probability to the other by a change of representation comes simply from the fact that Hermitian operators have a complete orthonormal set of eigenstates. And therefore, you can always find a transformation from one set of states to the other. In case of position to momentum, this is nothing but a Fourier transform. We now tackle one more point in this discussion, which has to do with destructiveness of measurements. So destructiveness of measurements. So the statement here, I'm going to draw a cartoon that we're going to use often. I'm going to draw a line representing time. And across the course of time, many things are going to happen. I think we've seen this already previously. But, at some point, I have my state of quantum system. So this is some kind of initial time. Whatever it is. And of course, at some later time, I have a psi of t, and the connection between these two is, of course, the time evolution. And then at some point, I perform a measurement, and I will denote the measurement as for instance, a little ball. So let me write down, note that this is a measurement of the quantity O And the result, let the outcome of O be OI, a particular eigenvalue. Then, after you perform the measurement, getting this value, the system will be immediately after in the state OI. And this is called collapse of the wave function. So basically, what I'm saying is that you have the wave function evolves its own ways, and we'll discuss later in which way does it evolve, according to the quantum evolution operator we defined at the beginning of this lecture. But what is certainly known is what happens soon after I do the measurement. Soon after I do the measurement, the system is in the corresponding eigenstates to the eigenvalue that I've detected experimentally. So this is actually the mathematical formulation of the famous Schrödinger cat story. You know, the cat is inside a box. There is a radioactive source inside the box with a cat. And if the source happens to decay, it triggers some kind of machinery that releases poison and kills the cat. And as long as the box is closed, you never know whether the cat is dead or alive. Or when you open the box, the cat is either dead or alive, and the wave function of the cat collapses to the result of the measurement. Now, this is a sort of a pictorial and picturesque anecdote and an analogy that has been used quite improperly because cats are macroscopic objects. They don't have a wave function, coherent wave function, and therefore they don't really behave quantum mechanically. In fact, you know, to the objection, the cat certainly knows whether it's dead or alive. It's very little to reply, and the reason is that the cat is in fact a classical object made by many, many microscopic objects. But an electron, of course, is an entirely different story. And we've seen from the experiment in Stern-Gerlach that, you know, this rule comes from the analysis of experiments such as the Stern-Gerlach. So let's for a moment connect this concept to the Stern-Gerlach. We have a beam. The electrons can be in any state of a magnetic moment here. Let's call it psi. Then the measurement is the Stern-Gerlach. The Stern-Gerlach performs the splits, and say my electron goes up. Then from that point on, if the electron has gone up, it means that the state will spin magnetic moments up along the z-axis. So if immediately after you have done this, you do another experiment very shortly by, you still expect to find the same result, still along the z-axis, because your system is in the same eigenstates of the magnetic operator, up, because that was the result of measurement. Measuring the wave function has collapsed the state into their corresponding eigenstates. But if I measure this state, perform another measure, this time, say along the Stern-Gerlach in this direction, I'm measuring the x component of the x component of the magnetic moment of the particle. And after I measure the x component of the magnetic moment of the particle, say the particle splits, say to the left instead of to the right. You have two options, left or right. But now I'm in an eigenstate Cx. Say if here I was in eigenstate C up, here after the splitting, I'm in the eigenstate C left. And if I measure the z component again, I have from Cx 50% probability to find C up, C down, and have to recollapse the wave function. So this idea of collapse of the wave function induces the concept of destructing the wave function's information after measuring it, because you sort of have, you know, the system collapsing to a very specific state, the one that you measured. Now, the question I'd like to address now is what happened happens to quantum states after they are measured. What do I mean? I know that in the moment of measurement and finding the result, say OI, my states is collapsed to the corresponding eigenstates. I find OI, my state psi at that particular time is in fact this state. What about later times? From there to the next measurement. Now this is an important information because maybe I make the measurement time t, and I want to know the probability of getting the same measurement after some time t prime greater than t. How do I find the probability of finding a certain measurement? So let's say at time t naught, I measure the operator O, and I find that the psi, after I find the observable OI, the outcome of the experiment is OI, and therefore at time t naught, the state is OI. And I would like to know the probability of observing OJ, a different value, J different from I, at time t prime greater than t naught, or t greater than t naught. Then clearly, we know the rule. This would be OJ psi of t, modulo square. But we know that we can connect psi of t to this state by quantum evolution, because remember, that's my time. At time t naught, I perform a measurement, getting as a result OI. Now the state here is OI. And at time t, I perform another measurement, for instance, of the same quantity. And I'm asking, what is the probability of observing OJ at this time t? I know that after this, the system will be in state OJ. But, what happens from here to here? Will the state remain in the same state, or we will go into another state or to many other states with different probability? Well, we can find out by applying the concept of quantum evolution we introduced at the beginning of this lecture. This is the evolution of a time t minus t naught of the wave function at time t naught. And the wave function at time t naught was OI because of the collapse of the wave function. Therefore, this is OJ u t minus t naught OI modulo square. It is still kind of an abstract expression. In general, there's very little you can say more than this, because you don't know really how to compute this evolution operator. In most general cases, what will happen to this quantum state from the time it is measured at t naught for the time it is measured the first time to the time it is measured at a later time, is that the quantum evolution will bring the state away from the original eigenstate into whatever linear combination of states with different. I can always write this, as a linear combination of eigenstates of a O operator, because it's an Hermitian operator and therefore it has a complete orthonormal basis. But I, in general, do not know what happens to these coefficients along the way, except in one case. However, if H commutes with O, then OI remains, so that the wave function psi of t remains OI for any later time until I perform a measurement. So at time t, the system will still be OI. How do I know? So in general, the wave function, after you perform a measurement of a particular observable, the wave function will evolve in its own way, and it's difficult to predict what will be the outcome of a measurement of a quantity. But under very special circumstances, well, that is when the observable quantities actually commutes with the Hamiltonian, the operator associated with the observable quantity that I measure at time t naught commutes with the Hamiltonian. Well, in that case, the wave function, the evolution of the wave function is trivial. It will remain in that particular state forever until you measure it again. And why is it that? Well, I can convince you about that because, let's take the time evolution operator of my state OI. Now, if H and O commute, then remember what we said in one of the last lectures, I can always find a common set of eigenstates, OI, that is simultaneously eigenstates of O and eigenstates of H. If two operators commute, then they have a common set of eigenstates and the different eigenvalues, of course, because the operators are different, but these vectors are simultaneously eigenstates of O and eigenstates of H. Well, then clearly I'm going to convince you that all that the evolution will do is basically rotate the phase of the state, which is unmeasurable. So stated differently, I'm going to convince you now that the probability of observing a different state, OJ, at time t, other than j not equal to I, well, or in general, a state OJ at time t, this is going to be 1 if I'm measuring the state OI, and 0 for any other state. In other words, the system remains in the same state. How come? Well, look, I can simply use this expression. There's an H bar here. Now, since this is an eigenvalue, if I have an operator and this is an eigenvalue of A, eigenstate of A, then this is going to be e to the A. How do I know? Well, all you need to do to prove this is to expand this as a series. And you see that immediately that when these collections of operators act on A, they will generate the corresponding eigenvalues. So at the end, I can re-exponentiate this to be this. So what this is telling me is that this concept here, this mathematical expression here, is going to be Oj e to the negative I over h bar t negative t naught ei o I modulus square. Now this is now a number, complex number, actually a phase, which I can take out, and I get this number. And then I get OI, OJ. Now this is a delta, because these two states are orthogonal, since O is an Hermitian operator. So all I'm left with is the modulo square of a phase, and the modulo square of a phase is 1. So this guy here, this is actually modulo square of a pure phase. So this is 1 times delta ij. So the final result is that this mathematical expression is nothing but delta ij. So what have I demonstrated? I've demonstrated that if a state, if the operator that I measure is a special operator that commutes with h, so a subclass of operators, then the quantum evolution of that state will be trivial. The system will remain the state forever. So this is, if you want, physically, how do I interpret this? This seems like a mathematical curiosity, because I've introduced this concept of commutation between operators. There seems to be very little physics behind this. But if you think about it sufficiently long, you realize that what these special operators that commute with the Hamiltonian are associated with special observables that are corresponding to conserved quantities. So what is a conserved quantity? Is something that, if you know it at time 0, it will remain the same for the rest of the dynamics. Remember, total angular momentum in the classical theory of the hydrogen atom, all you needed to do was to fix the angular momentum at time 0, because for the rest of the dynamics, you were ensured that the system would have stayed in the same angular momentum state forever. Now, what we are seeing here is precisely the same phenomenon. We are looking at, an observable O that commutes with h, and if you measure the result, if you measure the quantity O at time 0, and you find certain result, OI, then you're guaranteed that if you repeat the measurement any later time, letting the system evolve according to quantum evolution alone, you will still find the same result. Now, this very thing here has countless implications, even in quantum technology, such as quantum transcriptions. And I will get to quantum encryption, to those fascinating use of quantum properties for secure communication in the future, not in this lecture. This lecture is about rules. But this is important. So evolutions of quantum operators that commute with Hamiltonian is trivial. So let's go back to our set of rules. Let's go back to our set of rules and see what we get. Well, the expectation value is, of course, given in a quantum state, is given by this bra and cat. We already had this theorem stated in the previous lectures, and if psi is an eigenstate of O, then this average is simply trivially repeating the same result anytime you measure. And basically, everything that we said now in practice amounts to the following rule. In classical mechanics, observables are typically function of the state of the system, meaning they are function of position and momenta of all the atoms in the system. And if you're using coordinate representation, if you wanted to find, if you're interested in constructing the operator associated to a classical operator, you have to go through a process called quantization of operators. So what is that? Very trivially, suppose I have an operator that is a function, a classical operator is a function of momentum and position. For example, just to be practical, angular momentum is x dot p, right? X cross p, which, for instance, it means that LZ is, well, how do I know the three components? Well, let me do all the work. I, J, K, X, Y, Z, PX, PY, and PZ. So for instance, if I'm interested in the I components, that is the X, say, Y, and Z versor, then I have to do Y dot PZ minus Z dot PY, right? Now, this is a classical angular momentum operator, a classical angular momentum quantity. How do I construct the corresponding operator? Well, in a given representation, and we only need a classical, the coordinate representation, all we have to do is to replace momentum by negative partial derivatives. And we will find the corresponding quantum operator. We went through that when we were discussing the Fourier transformation, but that's the general rule in quantum mechanics. I'm just reviewing this rule. And basically, that's it. The rest of this is basically repeating concepts we have already discussed. So with this set of rules, basically, we are equipped to solving fundamental quantum mechanical problems. We have the set of rules that are required to formulate what it means to be making prediction in quantum mechanics. And if you want, the rest of this course will be devoted towards following the implication of this rule, possibly adding new elements concerning what happens when you have more than just one quantum particles. That has to do with statistics and concept of quantum statistics, and then the application to electronic systems. But other than that, I think this is the mathematical foundation of quantum mechanics and the overall setting. And basically, this is the set of rules that provide the very structure of this theory. Okay, thank you.